Hello students, now I found out this beautiful simulation software which one can use to understand basic shapes of molecules. Okay, so suppose this is one central atom. Let this to be any halogen. Okay, for sake of simplicity I am calling this as Cl. Okay, now if you join one bond to it, that means this is some H, and if you want to know what is the molecule geometry, then one can say it is linear. Okay. Now, if you add another bond to it, now for this I am calling this central atom to be Be, and the periphery atoms, which are these white atoms over here, to be as Cl. So this is basically BeCl2, and if you want to check what is the bond angle, as you can see over here, it is 180. Now let us consider another molecule. I'm calling this to be as hydrocyanic acid. Now suppose this is your carbon, this is your H, and that is your N. So between carbon and N there is a triple bond. And again, if you want to judge what is the bond angle between the triple bond and the single bond, it is around 180. Again, the molecule is linear shape. Okay. Now what you can do is rotate it and get a 3D view of this molecule like that. Now suppose we have finished our talk on central atom making two bonds. If I have three bonds, what kind of arrangement I can think of? Now this peripheral atoms are suppose taking the vertices of a triangle, and the purple atom is at the circumcenter of the triangle. The angles, now if you check, they are all 120. Okay, and since this is a triangle and it is lying, all the atoms are lying in one plane, as you can see. Okay, because they are lying in one plane, you cannot see the atom that is behind the purple one. Now if you rotate it, as you can see, so we will be calling this particular shape to be trigonal because it is in one plane, so planar. Okay, now what will happen if instead of a single bond we are having a double bond? So what we will do, we'll remove the single bond and we'll attach a one double bond. Now suppose I am discussing a molecule like phosgene, which is COCl2. Let us call these atoms over here Cl and that one to be O. So this is basically C double bond O. Now one has to remember as a student, again using the VSAPR, that if we compare the bond angles, say this particular angle and that particular angle, this is basically a multiple bond repulsion with a single bond. So if I call this to be as X, even this will be X. Now the repulsion between a multiple bond with a single bond will be more because multiple bond is having more electron density. So if this is X, that is X, and say this is Y, what will be the relation between X and Y? Will X be less or more than Y? We will say X will be having a higher value than that of the Y. Okay. Now let us go for another type of a molecule which we are calling as AB4 type, in which there are four sigma bonds, or the central atom is attached to 4 peripheral atoms. Now, as I attach 4 bonds, you can see this shape we are calling as tetrahedral. Now, if you consider the bond angles, each angle over here is around 109.5 degrees. Okay, and the atom over here is sp3 hybridized. Suppose instead of having a single bond over here, I want to have a double bond. Then what will happen to the angles? What will be the relationship between the bond angles? Which will be larger, which will be less? Let's do that. I have attached the central atom with another atom and they are making a double bond. In that case, if I am saying this particular multiple bond and this single bond, the angle over here, obviously, if I'm calling this as x, similarly I will call that angle to be as x. Again, this one also will be x, and all these values will be equal. Okay. And if I'm calling this angle over here as y, what will be the relation between x and y? Again, using the same logic, that multiple bonds repel more with a single bond in comparison to the single bond repulsion. So x will be having a higher value than that of y. Now, a good example of this molecule will be, if I consider the central atom to be P, this one to be as O, and all these atoms over here are Cl. So basically the molecule is POCl3. Okay. Now, what if I am having 2 double bonds and 2 single bonds attached to the central atom? For that, I will remove one single bond, attach one double bond. Now, a good example for this molecule will be SO2Cl2. Okay. Again, if one has to judge the angles, multiple bonds repel more. So if I'm calling this to be as again x, all right, I'm calling this angle to be as y and that angle to be as z. What will be the relationship between x, this y, and z? Again, according to VSEPR, multiple bonds will repel more. So this will be the highest angle, followed by the y. There is a multiple bond and single bond repulsion, and then we have the single bond repulsion. Okay, now what if we have the central atom making 5 bonds with the peripheral atoms? So for that, I'm going to remove the double bonds. Let's begin with a simpler one. Okay, now here, as you can see, this shape we are calling as trigonal bipyramidal. Which one is the trigonal? That atom, this one, and that one. They are making a triangle, as you can see. This is the triangle. And this particular bond and that particular bond are lying on the top and below with respect to this particular plane, that is the trigonal plane. So these bonds, as you can see, I am rotating the molecule. Okay. Now if you think This is like they are lying on the equator of a Earth, so they are called as equatorial bonds. And one can consider this particular bond along the z-axis. This is our axial bonds. In reality, this is a sp3 dehybridized atom, the central atom. The axial bonds, that is the one on the top and the one below, they are longer than the equatorial bonds, which are this one, that one, and that one. Okay, so this particular arrangement, we are calling it trigonal bipyramidal. Now, if you have a close look at the angles, what kind of angles are present over here? Now see, along the trigonal plane, these angles are 120. All of them are equal. Now so there are three 120-degree angles. If you consider how many 90-degree angles are there? That one, and that one. So on the top there are three 90-degree angles. Similarly, below there will be another set of three 90-degree angles made by this axial bond. So this one axial bond is making three 90-degree angles with the three atoms on the plane of the triangle, and below also a similar thing can be thought of. So there are six 90-degree angles for this arrangement. Now, if I remove one bond from here, and I think in place of that I am having a double bond, okay, just like that. All right. Now one correction over here, I have to place the double bond in the equatorial plane. Okay, so what I'm going to do is I am going to, okay, do we have the arrangement as we are thinking? Oh yes, we have got it. So now here you can see this particular double bond is in the equatorial plane. Okay, so this is exactly the arrangement that you will get for SOCl4 or SOF4. So if this is S, then that is the O, and the other Cl atoms which are more electronegative than the O will be taking up the axial positions. Okay, will be taking up the axial positions. Why? Because the Cl is more electronegative than that of the oxygen, and according to Bend's rule, the more electronegative atoms should be placed in the axial position. So if this is SOF4, oxygen will be in the equatorial plane because it is less electronegative than, say, fluorine or chlorine, and the axial positions will be taken up by the halogen atoms. Okay. Again, in terms of bond angles, if we discuss, previously when they were all single bonds, then this angle between the atoms in the equatorial plane all were exactly the same. That is equatorial. That is 120, sorry. But now, again, with the similar logic, that the repulsion between a multiple bond and a single bond is more, one will expect this particular angle to be more than 120 and that to be less than 120. Now, having discussed trigonal bipyramidal geometry, the other arrangement that could have been possible, but it is difficult to show here, is going to be square pyramidal. There also we will be having hybridization as sp3d. So it will be basically a square and there will be one bond on the top. Now what if there are six bonds? What kind of arrangement can we think of? So this particular molecule wherein it can be some SF6, okay, where sulfur is in the center and fluorine is at the periphery. So these white atoms are fluorine and purple atom is your sulfur. And the shape of the molecule over here is obviously octahedral. Now, if I rotate the molecule for you, you can see how it is like. Now here, this particular atom, that one, and that one, they are lying on a square plane, and we have two more atoms on the top and below. So in terms of bond angles, we know if this is a square, and we can consider these bonds as to be the diagonal. So diagonals bisect each other. So one can think this is 90, that is 90, that is 90, at the back that is 90, which can be shown. As you can see, all of these are 90. Now if I consider that shape, then this is 90, even that is 90, that is 90, that is 90. So in total there are how many 90 bond angles? We will say 8. Okay. And the hybridization of this central atom over here is going to be sp3d2. Okay. So that is all about the basic shapes of molecules. Now, I will take some real molecules to just discuss the molecules that I had given you. So for a BeCl2, as you can see, it is linear. One can do this one also. If you want to have a trigonal planar geometry, you can use your BF3 as an example. If you want to have a tetrahedral molecule as an example, it can be NH4 plus, BF4 minus, PCl4 plus. The list is endless. So that is your tetrahedral shape of CH4. Again, this is your phosphorus pentachloride. This is your trigonal plane including these atoms, and this is your axial bond, top and below. And as I have discussed, the hybridization of the central atom over here is going to be sp3d. And at last, we have our SF6. Okay. So that explains it. Thanks for listening and have a great day.